However, I have to start over. Okay, so we're going to review moles and stoichiometry and how to relate all these parts and pieces so you have a successful quarter. This is a question from the final exam that I gave. The students were told that nitric oxide is produced from reacting ammonia and oxygen. So ammonia, NH3, and oxygen, O2. Remember, oxygen's a diatomic. And we get nitric oxide and water, so our 6H2O here. So the first thing they had to do is balance it, which is fine. You can do that. It might take a little patience, as you know, some of the coefficients are not quite as pretty. But we come down here, and the first thing I'm kind of walking you through is determining your limiting reactant. And you're going to have to bear with me because for the rest of the video I didn't bring up my key, so I'm going to have to actually button push all my answers. So in this one, first it was how many moles of NO could be produced from the 75 grams of ammonia. So this is saying if I could react all of my 75 grams of ammonia, how much nitric oxide would I get? How many moles? And so I'd start off with the mass that I've been given of my ammonia, and then the molar mass, so 1 mole of ammonia, I gave the molar mass up here, there we go. 1 mole has 17.04 grams of ammonia, and then the next step was to look at our stoichiometry and do our mole-to-mole ratio of both. So there's a couple things that I want to point out, especially as we're moving on, is that I explicitly wrote out my grams ammonia, moles ammonia, moles ammonia, moles NO. What will not be acceptable is if I just see like 75 divided by 17.04 done. You have to show your work, you have to show your scientific thinking from how you get to from point A to point B for your answers to be counted and graded appropriately. Okay? So in this one, I finish and I say, okay, so this was 4.4 moles of NO. And then the next step is to do the same with oxygen. So I was told that I have 150 grams of oxygen. Make sure you can see that. So 150 grams of oxygen, O2, times, and I gave you the molar mass of it, times 1 mole of O2 to 32 grams of O2. And the same thing, we want to know how many moles of nitric oxide. So I come up here, and you go ahead and pause it and make sure that you can set this mole-to-mole ratio up correctly, and then come back. Okay? So I look here and I say I want my mole of O2 on the bottom because it needs to cancel out. I come back up to my stoichiometry. There's 5 moles of O2 in this chemical reaction to 4 moles of NO. 4 moles of NO. Now I can button push that in and find out how many moles of O2 I would get. So 150 times 4 divided by 32 times 5. 3.75. So 3.75 moles of NO. Button push that again. 150 times 4 divided by 32 times 5. Yep, I'm going to get it twice. So we're good. So that means that my oxygen is my limiting reagent. The most that I can get is that 3.75 moles of nitric oxide, which is fine. So that means that I'm going to have leftover ammonia. So I'm going to show you one trick that we can do here, and because we're going to subtract like from like, I can say, okay, so the most I'm going to get is 3.75, and if I do the math, my 4.4 moles of NO minus my 3.75 moles of NO will give me how many moles of NO I don't produce because I have this in excess. So I have ammonia in excess. So this difference here is going to give me the amount of moles that I won't create. And we're going to see why that's important in a second. So 4.4 minus 3.75 gives me 0.65 moles. And let's just go ahead and change the page. So we already said the limiting reactant was O2. And what mass of NO, or what is the mass of the nitrous oxide produced in this reaction? And actually I'm going to skip down to here because we just did that. 0.65 moles of nitric oxide. Let's turn this back into what I have in excess. So remember, my ammonia was in excess, so I know how much nitric oxide wasn't produced because there was excess ammonia. So I'm just going to work this in reverse. I've done that 0.65 moles, I already forgot, and we're going to do this mole-to-mole ratio in reverse to get to moles of NH3, and then I can do my molar mass. So, because I don't want to flip back and forth, let's just go ahead and do it here. I have 0.65 moles of NO times 4 moles NO to 4 moles of NH3, and if you wanted to write that as 1-to-1, that's fine too, if you wanted to simplify it. Now we want mass of NH3 because that's what we started with, our mass of ammonia. We didn't start with moles of ammonia, so to know how much I have left over, I have to do that conversion there. So we'll go ahead and put the 1 mole of ammonia on the bottom to the molar mass of ammonia on the top. So the molar mass of ammonia is 17.04 grams ammonia. And let's check our, well, things cancel out. Mole ammonia, mole NO, mole NO, and that will indeed give us grams of ammonia. So now we button push it. So 0.65 times 17.04. Now notice when I was talking that through, I looked at the top, these become 1, 4 divided by 4 is 1. So the only thing going on here is the 0.65 times the 17.04. I'm not worried about what I'm dividing by here. And so I get 11.076 grams of ammonia. And then the question is, how much do I have left? How much is in excess? And I come back to the original question, and I'm told that we started with 75 grams of ammonia initially. Oh, sorry. I'm doing this backwards from what I'm used to. We just figured that out. We're good. So let me clarify where I was going wrong on that. This is how much ammonia is left over. So because this is slightly different, some of you guys showed me something I hadn't actually seen before, and that was this approach here. Right? And in this approach, we say, looking at the difference between the two, this is how much won't be produced. Therefore, when I do the mole-to-mole ratio, that gives me how much is left over. So conversely, this is the way that I'm used to doing it. I say I have 3.75 moles of NO that will be produced, and I'm going to go ahead and do my mole-to-mole ratio, getting the moles of NH3, just like I did before. So 4 moles NO to 4 moles NH3 times 17.04 grams of ammonia per mole ammonia, per 1 mole ammonia. And let's see what that gives us. So we're going to get how many grams we actually consume in this question. It's 3.75 times 17.04 gives us 63.9 grams used of ammonia. So now to find out how much is left over, now we do the step that I was getting ready to do out of habit. I have 75 grams of ammonia that I started with, minus my 63.9 grams used. Hopefully you're seeing the pattern there. 75 minus that, and bada bing, I get 11.1 grams left over. It's magic. So there's two different ways that you can look at calculating your excess, and it really depends on which one makes most sense to you. But they both get the same answer. So with sig figs, this would be an identical answer to the first one we got. So that's how much is left over. And then we'll just go ahead and quickly do the mass of NO produced. So the mass produced, we know that we have that 3.75 moles. Oops, slide that up. 3.75 moles of NO times the molar mass that you were provided times 30.01 grams of nitric oxide per 1 mole of nitric oxide. So I took my limiting reactant, and my limiting reactant said the most NO that I could produce was the 3.75. That's a perfect reaction. Running to completion, I would generate 3.75 moles. So now I want to know what's the mass that I'll produce. 3.75 times 30.01, and I get 112.5 grams. Now in another video, we'll get a lot more explicit with working with our sig figs. But just a quick glance, nope, with the 75 grams, so we'd be down to 2 sig figs on this. Oh, that would be ugly. Yeah, so because our first digits, or our first values were 75 grams, there's no 0.0 after that. So 2 is my limiting to get there. Huh. So that is this, and then the next one we'll do is going to be explicitly with molarity.